Hi. Now in this video lecture we will be writing down the electronic configuration of some molecules, right, based on what all we have learned in previous video lectures, and then we will also look how to draw the energy level diagrams and then deduce the properties of molecules like bond order, bond length, right, and whether the molecule would be stable, will exist or not, right. Now let's look at it quickly. We have done, for one example we have already taken of hydrogen, right. Now we'll take the example of helium, right, helium molecule He2. We know that helium molecule doesn't exist, right. We'll prove the same using molecular orbital theory, right, by writing the electronic configuration of molecule helium. We know helium has 2 electrons, right. So helium molecule, right, which is made from 2 helium molecules, atoms, I'm sorry, it has only s shell, I'm sorry, it has only one shell, k shell, right, and k shell n is equals to 1, it will have only one subshell, right. So it has 2 electrons in this helium, 2 electrons in this helium, right. So total you have 4 electrons, right, in helium molecule. You have to distribute this 4 electrons in molecular orbitals, right. So how many molecular orbitals will get formed when s orbital of this helium, right, will overlap with, when 1s orbital of this will overlap with 1s orbital of this, it will form sigma molecular orbital and your sigma star molecular orbital, right. This is your bonding molecular orbital, this is your anti-bonding molecular orbital, right. And if you draw the energy level diagram, it would be like this. Right, it would be this is how it will look like. 1s orbital, 1s orbital, right, 2 electrons in this orbital, 2 electrons in this orbital. So resulting molecule which is shown in the middle, and you have this kind of arrow in energy level diagrams where that shows that energy is increasing, right. So orbitals that are going up have high energies, right. So here you have 1s orbital, because this is a bonding molecular orbital, it has lower energy. This would be anti-bonding molecular orbital, high energy. So 2 electrons, it has total 4 electrons, and each orbital can accommodate maximum 2 electrons. So 2 electrons will go here, 2 will go here, right. Now if you look at the stability, the condition for stability is that number of electrons in bonding orbital is greater than number of electrons in anti-bonding, but here 2 electrons in anti-bonding, 2 electrons in anti-bonding, Nb is equals to Na. This is your the value, or since both electrons are same in both the orbitals, right. So what you have due to this, an unstable molecule. The effect of bonding electrons would be nullified by the presence of electrons in the non-bonding orbital, right. That is why this molecule is unstable, right. Now let's look at this molecule He2 plus, right. First of all, let's look at the other properties. Let's look at, this is your stability, second is your bond order. Bond order would be half Nb minus Na, right. So bond order is again 0, that means unstable molecule, right. So what would be bond order 0 means there is no bond between two helium molecules, between two helium atoms. No bond means molecule does not exist. Bond length. Bond length, we don't see any bond, so no question of bond length. Right? No bond length. What about magnetic behavior? If you want to look at the magnetic behavior, for magnetic behavior, it is dimagnetic. Why dimagnetic? Because you have all the orbitals filled. All orbitals are filled. So this is dimagnetic, right? And would be repelled by the magnetic field since it is dimagnetic. Let's quickly look at, if I make this molecule, does helium ion exist? 1 plus shows that 1 electron is removed from helium molecule, right? So if I remove 1 electron, helium molecule has 4 electrons. If I remove 1 electron, it will form He. Let me write it over here. Helium molecule has 4 electrons. When you remove 1 electron, it will form helium ion, whether this exists or not. Stability. What about its stability? So if you draw the energy level diagram, 2 electrons you will fill up here. Now here you have 1 electron. In anti-bonding molecular orbital, you have 1 electron, because 1 electron, this has higher energy, so electron can be easily removed from this higher energy orbital, right? So as far as stability goes, this is N. Now we have the situation Nb is equals to 2 electrons and Na is 1 electron, right? So Nb is greater than Na. This shows the molecule is stable, right? And if you find out the bond order would be half, right? 2 minus 1, half bond length. Molecular orbital theory also tells you that, that there can be half bond or 2.5 bond between molecules. So half bond means somewhat stable. Somewhat stable. This is not, the stability is not very high, but it is somewhat stable, right? So this is helium ion and helium molecule. From this we know that helium does not exist. Helium molecule does not exist, right? Now let's take example of some other molecule. Let's take nitrogen, right? We know that nitrogen is formed from 2 nitrogen atoms, right? And each has 7 electrons. So in total you have 14 electrons. So now you have to distribute these 14 electrons based on this sequence, right, in various orbitals. So let's write down the electronic configuration of nitrogen molecule, right? So electronic configuration for nitrogen molecule would be, first sigma 1s2, sigma 1s, sigma star, then 1s2, then you have sigma 2s 2, sigma star 2s2, right? 1 2 3 4 8. Then you have pi 2px2, right, equal to pi, you will not put equal to here, pi 2p y2, right? Then the last one is sigma 2pz2, right? So here you can count 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So you have distributed 14 electrons in various orbitals, right? So this is the electronic configuration of nitrogen molecule. Let's look at its stability. Stability is how many electrons in bonding molecular orbitals and how many electrons in anti-bonding molecular orbitals, right? You have 2 electrons in this anti-bonding molecular orbital and 2 in this, right? So it would be 2 4, 5, 6, 7, 8, 9, 10. 10 electrons in bonding molecular orbital, and in anti-bonding you have 4 electrons, right? So here Nb is greater than Na. This means it's a stable molecule, right? That means it's a stable molecule. Let's look at the bond order quickly. Bond order would be half Nb minus Na, half 10 minus 4. It will come out to be half into 6 equal to 3. Bond order 3 means nitrogen has triple bonds, 3 bonds, right? So likewise its bond length will decrease, because we know bond length is inversely proportional to bond order, right? Let's look at its magnetic behavior. Magnetic behavior. Now magnetic behavior would be, you can see that all the orbitals are filled, right? Since all the orbitals are filled, no orbital is left with half filled. No orbital is half filled. That means the magnetic behavior, it is dimagnetic. Dimagnetic means it would be repelled by magnetic field, right? So these are the properties of nitrogen molecule that we already know, right, and is now proved from molecular orbital theory. Now let's look into the other example. The other example is oxygen molecule, right? Oxygen molecule, each oxygen atom now has 8 electrons. So you have total 16 electrons that you need to distribute. Okay, one more thing. You can have like this molecules, like if we talk about ions of nitrogen molecule, if I talk about N2, right, N2 plus, N2 minus, N2 2 minus, right, then what? If I take N2 plus, right, whether this molecule exists or not, right? If I take N2 plus, that means I'll remove 1 electron from here, right? So electronic configuration of N2 plus will become, here you have total of 13 electrons now. So here you have 1 electron, right? So still Nb is greater than Na, it exists, right? And if you talk about bond order, it would be half 10. It would be again now 4, this will become 9, right? So here you have 9 minus 4, it will become, this is like 2.5 or 2.5 bond, right? So the molecule exists, is stable, right? And what about its, these are 2.5 bond. Like I said, molecular orbital theory is a little advanced theory, and it does tell us that even a half bond exists between the molecule, right? And when we talk about its magnetic behavior, now it has one unfilled orbital, half filled orbital, I'm sorry, right? You have 2pz1, this is a half filled orbital, right? So what would be its magnetic behavior? It's a paramagnetic molecule. By saying paramagnetic molecule, that means it would be attracted by the magnetic field. Right? Similarly, if I talk about N2 minus, right, in case of N2 minus, in case of N2 minus, that means it has one extra electron now. Earlier the electron was removed, now it has extra electron. So what will be its electronic configuration? It will be 2, it will remain 2, right? Now you have to add, if you look at here, earlier electronic configuration ended at sigma 2pz here. Now you have added one electron extra which will go here in pi molecular orbital, which is anti-bonding. Pi star 2px1, right? So what would be its stability? Nb is still greater than Na, it will exist, and its bond order would be half. This will become, number of bonding electrons will remain 10, anti-bonding will become 5, right? So it would be 10 minus 5, 5 upon 2, it's 2.5, again 2.5 bond, same as this ion, right? Two and a half bond. And what about its magnetic behavior? Magnetic behavior, you have one half filled orbital, anti-bonding orbital, so it would be a paramagnetic, right? Paramagnetic, same as N2 plus, right? So this is clear. Similarly, if you have, say, N2 minus 2, right? So I'm adding one more electron now, right? And this electron will go to the same, right? This electron will go to either it can go to px, to pi 2 px, or you can even, because both have same energy, so it can go to pi 2 py, right? So we'll add it to pi 2 py. So we have one more anti-bonding electron in that case, right? So we will have one more anti-bonding electron, right? So NB, it's so this electron will again be added to, the extra electron will be added to this orbital, right? So what would be its magnetic behavior? Two half filled orbitals, it will still be paramagnetic, right? So you can add one extra electron here, it will become 10 minus 6, right? 10 minus 6, you have one bond, single bond in this, right? You will have only single bond in this molecule, because it would be half 10 minus 6, right? Half 10 minus 6, it will become half into right? So this is how we can keep adding electrons in various orbitals, and from there you can find its magnetic behavior, its bond order, right? So I hope this is clear. We will do one more molecule. We will do it for oxygen molecule as well, right? So just remember that this is still a paramagnetic molecule, right? And here you have added just one more electron in anti-bonding molecular orbital. So anti-bonding molecular orbital will increase by 1, right? So it will become 6, right? So you have kind of a double bond there, right? Bond order would be a double bond. 10 minus 6 would be half into 4, it's 2, double bond in this molecule, paramagnetic, right? I hope this is clear to you. Now I just want to show you one thing, that in some of the books you will see that this part, since this means an inner shell, right, the first shell, this part would be replaced by K, right? So instead of writing this, you will see that they will, somewhere it is written K, right, or KK. That means these are non-bonding electrons. Since these are non-bonding electrons, you can replace this with KK, right? And even in energy level diagram, you will not show this part, right? Because this part shows non-bonding electrons, that is the electrons that does not take part in bonding, right? For molecules like nitrogen, oxygen, but not so with hydrogen, because it has only one shell, so you cannot remove it, right? So somewhere you will find that this is replaced with KK, this sigma 1s2, sigma star 1s2, right? So you can calculate likewise the rest, right? So I have calculated, I have done all these calculations including these two electrons also, right? So I hope this is clear. Let's quickly do it for oxygen molecule, right? Oxygen has it has 8 electrons, right? So you have to distribute those electrons in the various orbitals, and for oxygen the sequence followed would be little different than this, like I discussed in the last video lecture. Right? For oxygen molecule, you have 8 electrons, right? Each oxygen atom has 8 electrons, so total you have 16 electrons, right? Oxygen molecule is formed from oxygen atoms, each has 8 electrons, so you have total 16 electrons that you need to distribute in various orbitals to write down the electronic configuration for oxygen molecule, right? Let's just write it down here, sigma 1s2, right, sigma star. So we can replace this part with KK, we don't have to write this, we'll replace it with KK, right? Then comes your sigma 2s2, right, sigma star. So likewise you have now 14 electrons that you need to distribute, right? 2 electrons go in K shell, 4 electrons will go in the K shell, right? So here sigma 2pz will come first, then your in this will come first, right? Or you can write it like this, you can write it, then we'll later replace it, sigma 1s2, sigma star 1s2, right? Sigma star similarly 2s2, right? Then this will come first because this follows a different sequence. You have 2, right? Then you have pi 2px 2, right? So 1, 2, 3, 4, 5, 6, right? And pi 2py, after this comes your pi 2py, right? Then comes your pi star 2px 2. Here you have 2, 1, 2, 3, 4, 5, 6, 7, 8, right? So you have distributed 8 electrons. So how you distribute in these degenerate orbitals? 1 electron in each. Here you have 1 electron, then you have pi star 2py 1 electron, right? This is how you will distribute electrons in these subshells, in these orbitals, I'm sorry. So let's quickly see the properties of this molecule, oxygen molecule, right? Let's look at the stability. Stability is number of bonding electrons and number of anti-bonding electrons, right? So if you can write down the similar configuration replacing this with kk, then sigma 2s 2, sigma star 2s 2, then rest of that, right? This is what I mean, because these are inner shell electrons, these are non-bonding electrons or non-bonding orbitals, right? So you can replace this always with kk, and similarly this part will also be replaced. I mean, we will not write this part, this represents non-bonding. You can start your energy level diagram from here, right? So you have how many bonding electrons you have, right? You can just calculate, add it up. You have 1 in sigma 1s, 1 2, right, 3 4 5, right? You have 10 electrons. And how many anti-bonding electrons? So 1 sigma star 1s, sigma star 2s, then pi star 2px, pi star 2py. Total you have 6 anti-bonding electrons, right? Bonding electrons 10, anti-bonding electrons 6, right? So Nb is greater than Na, right? That means the molecule is stable. What is bond order? It would be 10 minus 6, which will come out to be 2, right? We know oxygen has a double bond. And what about its magnetic behavior? Magnetic behavior is, it's 6. I'm sorry, magnetic behavior is all are filled orbitals, right? You can see all are filled orbitals, but these two pi star 2px, pi star 2py, these two are half filled orbitals, right? So half filled orbital means this has magnetic properties, this is paramagnetic. Why paramagnetic? Because you have two half filled orbitals and this would be attracted by the magnetic field. Attracted by magnetic field. Similarly, you can have ions like we did for nitrogen. You have N2 plus, N2 minus, right? Same you can do with oxygen. You can take these molecules O2 plus, O2 minus, right? O2 plus, O2 minus, right? And O2 2 minus. O2 plus means you are removing one electron from here, it will still remain paramagnetic, right? So one electron will become less in anti-bonding, right? It will become 5, right? So its bond order will become half, 10 minus 5, it will become 2.5, right? And what about O2 minus? In case of O2 minus, you are adding 2 extra electrons, so this will also get filled up, right? This will also get filled up. So you have 2 more anti-bonding, 8, this will become 8, right? So half 10 minus 8, right? A bond order will become 10 minus 8, it will become 1. You have single bond in this. Similarly, what would be its magnetic behavior? If you fill up this, right, you still have these half filled orbitals, this will still be paramagnetic, right? Like that you can reduce all its properties like we have done, right? So I hope all this is clear. Just know how to write down the electronic configuration, right? Once you know how to write down the electronic configuration, and remember one thing, for oxygen molecule we have taken this before, right? 2pz, because this is of higher energy compared to these two, right? Sorry, this is of lower energy, so this will come before. For nitrogen, this has higher energy, right? So this will go after this, 2px and 2py, right? I hope this is clear. Just you can